Ever clicked search on a massive website and gotten an answer in like a split second? Well, we're about to pull back the curtain on the hidden mechanics that make that incredible speed possible. It's a journey deep into how data is physically stored, a story of smart packing, clever maps, and one truly amazing data structure that basically powers our entire digital world. You know the feeling, right? You hit search on some huge data set and you just wait. It's so easy to blame the sheer amount of data, the terabytes and terabytes of information. But what if I told you the amount of data isn't the real problem? The real bad guy here? It's something else entirely. Yeah, the true performance killer, the thing that slows everything down to a crawl, is something called I/O cost. It's not about how much data there is, but about how many times we have to physically go and fetch it from that slow spinning hard drive. Okay, so here's the deal, and this is absolutely crucial. Getting data from a physical disk is literally thousands of times slower than getting it from memory. Every single time the database has to read from the disk, it grabs a fixed-size chunk we call a block. So the I/O cost is just the number of blocks we have to grab. Our whole game plan, our entire mission, is to make that number as tiny as humanly possible. All right, so let's start at the very beginning. Think of these disk blocks like little shipping containers for our data. The first big question we have to answer is, what's the smartest way to pack our data records into these containers? So right off the bat, we've got a big decision. On one side, we have the unspanned approach. This means if a record doesn't quite fit in the space left in a block, we just leave that space empty and start a new block. It's fast, because a single record is always in a single block. But you can see how it wastes a lot of space, right? The other way is spanned. Here, we'll actually split a record across blocks to use every last byte. No wasted space, which is great. But now to read just one record, you might have to fetch 2 or even more blocks. And that means a higher I/O cost. And right there, that's one of the most fundamental trade-offs in all of computer science: space versus time. Do you optimize to use every last little byte of your disk, or do you optimize for the absolute fastest retrieval? There's no single right answer. It's always an engineering decision. Okay, so we figured out how to pack our records into blocks. But now, how do we find the right block? How do we find the one with the user you're looking for without having to open and check every single one? Well, the answer is we build a map. This is the perfect way to think about it. Searching a database that doesn't have an index is like trying to find a specific sentence in a novel by reading it from page 1 all the way to the end. An index, on the other hand, is like the index at the back of the book. It's a smaller, separate guide that lets you look up a word and tells you exactly which page, or in our case, which block, to jump to. Now, these maps come in a few different flavors. If your main data file is already sorted, like by user ID, you can use something called a primary or clustering index. These can be sparse, which is super efficient. Because the data is already in order, you only need one entry in your map for each block of data, not for every single record. But if your file is a total mess, completely unordered, you need what's called a secondary index. And this one has to be dense, meaning it needs an entry for every single record. So this all sounds great in theory, right? But what's the actual real-world impact? Let's look at the numbers, because this is where you'll see just how crazy the difference is between searching with and without an index. So let's picture this. We've got a file with 30,000 records. With no index, our only option is to just start at the beginning and check every record one by one. On average, you'd have to read about half the file, which in this case means fetching around 1,500 blocks from the disk. That is a huge I/O cost. And for the user, that just feels like waiting forever. Now, get ready for this. With a simple 2-level index on that exact same data, we can find any record by accessing just 7 blocks. We went from 1,500 disk reads down to 7. That's not just a little better, it's a complete game changer. That right there is the power of indexing. So indexing is amazing. We solved the problem. But of course, databases aren't static. People are adding and deleting things constantly. So what happens when our map, the index file itself, gets so big and messy that it starts to create its own performance problems? Yeah, these simple static indexes have some pretty serious weaknesses. If you want to insert a new record into a sorted file, you might have to shift literally millions of other records just to make room. When you delete records, you leave behind all these empty holes, just wasting space. And to handle new data, They often create these overflow pages, which are like a messy chain of sticky notes you have to follow just to find your data. It gets slow fast. So this brings us to the holy grail of database design. The big question becomes, can we build an index that's alive? Can we build one that's dynamic, that cleans up after itself, and that stays perfectly balanced and efficient no matter how much we throw it at it? Well, the answer is a big yes, and it comes in the form of this absolutely brilliant data structure called the B+ tree. It's a dynamic, multi-level index that has become the gold standard pretty much everywhere, precisely because it solves all these messy problems. B+ trees are basically made for this job. First off, they're incredibly wide and shallow. This keeps the height of the tree super low, which is the key to minimizing block access. Second, they're self-balancing. When you add or delete data, the tree automatically splits and merges its nodes to stay in perfect shape. And maybe the coolest part? They're block-aware. Each node in the tree is designed to fit perfectly inside one single disk block. Now, hold on. It's really important to get this next part right. There's the B tree, and then there's the B+ tree. They sound similar, but there's a huge difference. In a B tree, pointers to the actual data can be in any node. But in a B+ tree, all the real data pointers, they're only at the very bottom level, the leaf nodes. All the nodes above them, they're just lean, fast signposts for navigation. This means the signpost nodes are smaller, so you can pack way more of them into a block, which makes the tree even wider and shallower. That's the key to minimizing I/O. And that design, it gives the B+ tree a superpower. All those leaf nodes at the bottom are connected to each other in a sorted, linked list. This is a total game changer for range queries. Think about searching for all products between $50 and $100. The database just finds the first $50 item, and then it just zips right across that linked list, grabbing everything it needs. It is incredibly fast. So how does a search actually work? It's way simpler than you might think. You start at the very top, at the single root node. Based on what you're looking for, you follow one pointer down to the next level. You keep doing that until you hit a leaf node at the bottom. There, you find your key, grab its data pointer, and make one final trip to the disk to get the actual record. For a database with billions of rows, this whole thing often takes just 3 or 4 disk reads. It's incredible. Okay, so that raises a good question. We keep saying these nodes are wide, but how wide are we talking about? How does the database figure out the perfect number of keys to pack into a single node, which, remember, is one disk block? It all comes down to something called the order of the tree, which we call P. P is just the maximum number of child pointers a node can have, and it's figured out with a simple formula that's really just a packing problem. Basically, the math just makes sure that everything you need for one node, all the pointers plus all the keys, fits snugly inside a single disk block. That's it. Let's make this real with an example. Say our block size is 512 bytes, our keys are 8 bytes, and our pointers are 4 bytes. We just plug those numbers into the formula. The math spits out that the maximum order, P, is 43. Now think about what that means. Every single internal node in our tree can point to 43 different children. That incredible branching factor is why B+ trees stay so incredibly flat and so incredibly fast. So let's just step back for a second. Isn't that fascinating? To solve the problem of finding data quickly, the solution was to actually create more data, this highly structured, intelligent index. This idea of solving a problem by adding a new, smart layer of abstraction on top of it is one of the most powerful patterns in all of computer science. It really makes you wonder, what other complex problems out there are just waiting for the right layer of abstraction to make them simple?